We all know that developing processes for biologics is hard. It requires juggling, or maybe balancing, multiple factors and their interactions to find the optimum process in the minimum amount of time. For CIP process development, you may be juggling the need for maximum protein denaturation and removal against the desire to minimize time and consumption of other resources. Thankfully, there's UNCLE. UNCLE is a flexible, multimodal biologic stability platform that combines 3 detection methods: full spectrum fluorescence, static light scattering, or SLS, at 2 wavelengths, and dynamic light scattering, or DLS. Those 3 detection methods can be used in 12 applications to help you understand the stability and aggregation behavior of your proteins. To test any of these applications, only 9 microliters of sample is needed, and up to 48 samples can be run at once. Importantly for CIP method development, UNCLE lets you control the temperature your sample is exposed to and uses fluorescence, SLS, and DLS to give insight into the way your protein responds. Here's a look at how our 3 detection methods enable UNCLE's applications. By using all 3 detection methods in unique ways, UNCLE can give insight into the impact of a CIP process on protein unfolding that is not available by using 1 or even 2 of these methods alone. For example, there's an application for TM as the first row of the table. With full spectrum fluorescence, you can monitor the unfolding of proteins by looking at the intrinsic fluorescence from the aromatic residues in your protein, mainly tryptophan. As your protein unfolds, that fluorescence signal changes as those aromatic residues experience a changing local environment. UNCLE tests this by applying a constant heat stress or doing a thermal ramp. From this type of experiment, you can get a melting temperature, known as a TM, which is a metric marking a protein's transition from folded to unfolded. Simultaneous with that fluorescence measurement, you can use static light scattering to monitor how the same sample aggregates over that same thermal ramp, and mark the temperature of aggregation onset as a protein's T-ag, which is seen in the table's second row. The other main application we'll be discussing today for protein characterization will be for uncovering a protein's sizing and polydispersity with dynamic light scattering. Together, these applications give information on protein stability and aggregation before, during, and after the elevated temperatures and chemical stresses of a clean-in-place protocol. Now allow me to introduce one of the key features of UNCLE, the UNI sample holder. The UNI enables UNCLE to gather all its information from a 9 microliter sample. Depending on the protein, you can work with concentrations as low as 50 micrograms per mil and as high as 150 milligrams per mil. The UNI is composed of an array of 16 quartz cuvettes that are easily loaded with a pipette. The high-grade quartz gets its great optical sensitivity for fluorescence and light scattering data, and the frame is made of a dark anodized metal that provides efficient heat transfer. The unis then go into this little blue holder that seals the samples on both ends. Because they are sealed when they go into the instrument, you don't need to worry about cross-contamination or evaporation, even for longer runs. UNCLE can hold up to 3 unis at a time, meaning you can run from 1 up to 48 samples in each experiment. One of the most powerful tools of UNCLE is its ability to monitor a protein's intrinsic fluorescence simultaneously with gathering SLS data to get the complete story of protein thermal stability and aggregation in just a single experiment. Here we're looking at the results of a thermal ramp experiment where protein fluorescence is being tracked in blue and SLS is in green. Fluorescence shows your proteins unfolding and quantifies that with melting temperatures shown at TM1 and TM2. The SLS data in green shows the aggregation behavior of your protein and reports the temperature when aggregation begins as a T-ag. The software's algorithms follow our zero-click analysis approach and it assigns these TMs and T-ags automatically. Together, the 2 protein tools of intrinsic fluorescence and SLS give you an understanding of how unfolding and aggregation is occurring in response to thermal stress. And not only do you know when your protein might unfold, but the TM and T-ag values can also be used as metrics for the characterization of a protein. Over a heat ramp, UNCLE will excite and read the full spectrum fluorescence of a protein sample at numerous temperatures. Each line in this graph is a fluorescence read of a protein excited at 266 nanometers, starting at 15 degrees Celsius, all the way up to 95 degrees Celsius. You can see by following the curves from top to bottom how they shift to the right side of the graph. This is the longer wavelengths. This phenomenon is called a redshift and occurs because the protein is unfolding and buried tryptophan residues have a shifting fluorescence emission as they move from being buried in hydrophobic pockets to being exposed to an aqueous environment. This protein shows a classic redshift pattern, but you never know how each protein will behave until you've tried it. Some proteins shift to the left, called a blue shift, while others can decrease in fluorescence without a shift. With this way of collecting full spectrum fluorescence, you have all the data and don't have to worry about unexpected protein behavior. For proteins without tryptophan, UNCLE also has a 473 nanometer laser that can be used with Cypher orange dye to excite fluorescence and determine unfolding. UNCLE gives you flexibility in analysis too. So not only do you get full spectrum information, but 4 analysis methods give you flexibility for those proteins that redshift, blue shift, or maybe don't shift at all. The analysis method we recommend reports the barycentric mean, or BCM, shown in the top left. This is the wavelength that evenly divides the area under the curve. We found that this analysis method is the least susceptible to noise since it analyzes a large range of the fluorescence data. For this presentation, all fluorescence data is analyzed to look at the BCM wavelength. Here we're looking closer at the use of static light scattering, SLS, to detect aggregation during a thermal ramp. Increasing scattering of the 266 nanometer laser gives us information on when smaller aggregates begin to form. We call this the TAG266. Likewise, since longer wavelengths scatter when hitting larger particles, SLS using the 473 nanometer laser gives us information on when aggregates begin to form, at the TAG473. Having information from both lasers at the same time gives you better sensitivity and a better detection range than with either laser alone.